Hey physics, welcome to another flipped lecture. We're moving into chapter 22 and the first part of that, chapter 22a today. We're talking about electromagnetism. So we've talked about electricity, we've talked about magnetism as a separate entity, and now we're talking about how the two cause and affect each other. So we're looking at electromagnets and electromagnetism today. Moving on, here we go. Just a quick review. We've already, when we were talking about magnetism, talked about the fact that magnetic field is formed according to a right-hand rule around a conductor. That background knowledge will be important for our discussion going forward today. So just remember the right-hand rule. If you were to grab a wire, don't do this if you're going to get electrocuted, but if you grab a wire and you put your thumb in the direction that the current is going, make sure it's your right hand because it's the right-hand rule, and your thumb goes in the direction of current flow, your fingers will wrap around the wire in the direction that the magnetic field is moving. So the magnetic field will be generated in this direction as your electrons move in this direction, right? So just as a reminder, that is the right-hand rule. You've seen that in physical science, and now you've seen it at least twice this year. So just as a reminder, there it is. If you were to take that coil of, or that wire, and bend the wire into a loop so that you had a wire that's like in the shape of the omega letter, where it comes up and then goes around like so. That loop of wire, because it's creating a circular magnetic field around the wire, if you now bend all those circles on top of each other, you wind up with something that looks very much like the magnetic signature of a bar magnet, where the field lines leave one end and loop around through space and hit the other end of the magnet. And so that is that's created by a loop of wire with a current running through it. That loop of wire is called an electromagnet. Most of us think of an electromagnet as wire spooled around some kind of ferromagnetic thing, like a nail or a bolt or some iron bar. And that is also an electromagnet. But the simplest structure that will behave like an electromagnet is a loop of wire, okay? And then you just pass an electric current through a single loop of wire and you have a very simple electromagnet, okay? Now, if you take a whole lot of loops and stack them next to each other, then the magnetic field will magnify depending on the number of loops that are there. And you don't have to have each individual loop be its own wire. It doesn't have to come in, go around and go out, and then have another wire come in, go around and go out. You can coil the wire, and each turn of the wire behaves as if it were its own electromagnet. And so an electromagnet made up of coils of wire is stronger than a single coil of wire by a factor of the number of loops. So if one coil of wire has a certain number of farads of magnetic energy, then, oh, you just used the wrong unit. It's not farads, I'm sorry. If it has a certain number of Webers of magnetic energy, then a loop with, or a magnet with 5 loops would be 5 times stronger. So a magnet with lots of loops is stronger by the factor of how many loops there are. And we call a magnet with several loops a solenoid. So solenoid is just a word for an electromagnet made up of many loops of wire. And that one magnet is 5 times stronger if it has 5 loops, or 100 times stronger if it has 100 loops, or something of that nature. Okay? So this would be a picture of a solenoid, and the one wire making several loops would have a magnetic field that is stronger than one loop by a factor of 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 loops. So 10 times stronger than a single loop. This is just an artist's rendition of what the magnetic field may look like around a solenoid. Okay, most of us think of an electromagnet, again, wrapped around some ferromagnetic material. And what that does is a ferromagnetic material magnifies an electric field. So if you are taking a magnetic field that's created by one loop and magnifying it by having multiple loops, and then magnifying it again by putting a piece of ferromagnetic material in the middle, now you have a very strong electromagnet. And you can make an electromagnet strong enough to be used in wrecking yards like this one would be, or this one is probably sorting metals from a ferromagnetic type of metal like iron or cobalt or nickel to some other, from some other kind of metal like aluminum or tin. And so this might be sorting that. But these very large electromagnets, powerful enough to pick up and move cars, these are very powerful magnets, and it's because of lots of turns of very high current wire around a ferromagnetic core. Okay. Wires with currents running in the same direction will attract each other. So if you have a wire laying next to another wire, and you pass a current going the same direction through those two wires, those wires are going to want to get together. They're going to be drawn together by complementary magnetic fields, because they're both moving the same direction. So if I've got a wire moving up and another wire moving up next to it, then the wire 1 is going to have fields going in this direction, and wire 2 is going to have fields going in this direction, and the loops will complement each other so that at one point the magnetic field is going like this around one wire and like this around the other wire, and those opposite magnetic fields will attract, and so the wires will want to slide together. Which is why fibers of a copper wire that are running in one insulation sleeve don't want to fly apart from each other, but as they are all carrying current, they actually stick tighter together. They're magnetically attracted to each other. That phenomenon has actually allowed us to redefine some electric terms that are hard to define otherwise. So an amp was some large number, 6.24 times 10 to the something big, number of electrons somewhere, right? Hard to count the number of electrons. Hard to measure what an amp is. But if we take wires that are magnetically attracted to each other, we can measure the magnetic attraction between two wires and determine how much current is flowing through those wires. So that's allowed us to redefine the amp into something that is a lot easier to measure. And the new definition of an amp for chapter 22 and forward is the amount of current which will cause two wires to attract each other at a distance of 1 meter with a force of 2 times 10 to the negative seventh newtons of force for every meter of their length. So if the wire is 1 meter long and its friend is 1 meter long and they're 1 meter apart from each other, and you pass current through them and they want to go towards each other with a force of 2 times 10 to the negative 7th newtons, then you have just passed 1 amp of current through that wire. Okay, longer wires would have a greater force, and so we've got to take into account the length of the wire. That has also allowed us to redefine the coulomb. The amount of charge that flows in 1 second past a point in a conductor carrying a current of 1 amp is 1 coulomb. So a coulomb is 1 amp per second. That's a lot easier than, again, counting electrons. So this is these are new definitions for these terms. The old ones that you had a couple chapters ago, it's not like they're not true anymore. They're still true. It's just a lot easier to measure this definition of an amp and of a coulomb of charge. Okay. And so just a picture to demonstrate that. You have a wire with current going in one direction and another wire with current going in the same direction. The magnetic field from this wire will be tails in between, where the magnetic field from this wire is tips of arrows, and so the tips of arrows and the tails will attract each other. And so the current in the same direction causes a magnetic attraction between the two, and the wires want to get close together, and we can measure that force. This is what's called a wire balance, or a charge balance. And so we have a power, we have a power supply creating a known amount of current, and we would pass the power supply through an ammeter to get an accurate measure of the number of amps, right? And then putting that into this apparatus here that feeds current through a wire, and then that wire has a parallel wire that's resting on a scale. So it's kind of a complicated thing to imagine, but here there's a wire and its weight is being transferred to the scale. And here's the other wire with a known amount of current going through it. So as the second wire, whose weight is on the scale, is attracted to the wire with the current, then we can weigh the force difference of how much the second wire is weighing down. It will weigh less as current goes through, and so we can determine how much less it weighs, use that to figure out the magnetic attractive force between the two wires, and verify the magnetic force to the reading of the ammeter. If you didn't get that, that's okay, but this is just the apparatus that we would use to measure the magnetic attractiveness between two wires. Okay. Electromagnetic induction. This is the phenomenon where you have one wire that is hooked up to a power source and another wire that is not hooked up to a power source. And we can pass a current through wire 1 and create a current in wire 2. Or you can also do it with magnets. You have a wire not hooked up to a power source, and you pass a magnet by it and you create a current of electricity. And that's actually the more important one for our applications here in this part of the lecture. You can take a magnet, pass it by a wire, and create a little bit of a current. Now the magnetic field has to be changing, so you can't just set a magnet next to the wire and get electricity. The magnet has to be moving with respect to the wire, or the magnetic field has to be changing with respect to the wire. And so this is called electromagnetic induction. You're creating a magnetic field change and getting electricity out of that. The fluctuating magnetic field creates a fluctuating electric potential, which creates current. So if you can continuously move a magnet by a wire, you can continuously create electricity, which is how we generate electricity 99% of the time. And so those moving magnets need to be moved by some outside moving force. But the goal of any kind of electric generator is to move a magnet next to wires and create electricity from that. Okay, that follows a mathematical formula called Faraday's Law, which is the only math equation this week, so yay for light math. But Faraday's Law is that the changing voltaic potential is equal to the changing magnetic field divided by time. So how much does the magnetic field change per unit time will give you how much electricity you're making. And we measure the magnetic field in units called Webers, and the unit or the symbol for that is the Greek letter phi or phi. It's the F sound or the PH sound in Greek. And so the symbol is the circle with the vertical line through it. That's the lowercase phi. And so delta phi is the change in magnetic field strength, change in magnetic flux, and we're going to divide the amount of change by how long that took, and that will give us the amount of voltage that we're creating, the change in voltaic potential that was created in that wire. The more rapidly the field is changing, the more voltage that is produced, right? Same delta phi divided by a smaller time unit will give us a bigger delta V, more voltage. So, but we can also work this backwards where we change the voltage and then make the magnetic flux change as a consequence, and that would be what happens in a motor. And then the magnet spins because of the changing voltage coming through the wires of the motor. So you can either make a generator or a motor. It's the same exact piece of apparatus. And here again, just a picture of this. We hinted at this in the last couple of chapters, but just one more time. You can take a magnet, run the magnet up and down through a coil of wires and get voltage out of that. Or you could have one coil of wires with their own magnetic signature because of the current and run that loop of wire in between another loop of wire and induce voltage that way. Or if you have this loop of wire already inside another loop of wire, just turning it on and off will change the magnetic field and induce voltage. So you can do that 3 different ways. But anytime magnetic field changes around a loop of wire, the wire creates electricity for just a moment. Okay. And here's another picture, and this is supposed to be an animated GIF, and I don't know why it's not animating, but imagine the magnet running back and forth in your mind. Sorry, this isn't animated. And as the magnet runs back and forth, the voltmeter should bounce back and forth between the two sides of the voltmeter, because as the magnet's going in, it'll create one kind of charge, and as the magnet is coming out, it'll create the other kind of charge, which is why we get to AC currents here soon. Okay. And then a generator works this way by taking magnets and spinning a loop of wire between the magnets, and then as the wire approaches one side of the magnet, one pole of the magnet, it will experience one direction of electric current flow, and we will get one kind of voltage potential on this side of the wire. And then as the wire approaches the other pole of the magnet, we'll get the other direction of voltage potential and the other direction of current flow. So by separating the wire into two halves and having these split rings where the wire touches this side only as it's approaching the north pole and touches this side only as it's approaching the south pole, then we create a constant flow of electricity. It doesn't go back and forth. We create a DC flow, direct current flow. Otherwise, we'd be creating a back and forth flow, which is alternating current. Okay, and we'll get more into that next week. But for now, you've just seen the consequence of Faraday's law. Okay, last one, Lenz's law, and this one has to do with just one loop of wire and its neighboring loop of wire. You power one, you don't power the other, and we can induce an electron flow in the second wire with the electron flow in the first wire, and we're looking at the magnetic interaction between these two wires. I'll show you some pictures in a minute. But if you induce a changing magnetic field from an electric flow in one wire, a second wire sitting next to it will momentarily have an electric flow as the magnetic field is created or changes or goes away, and that second wire will then be induced to have a magnetic field and induced to have an electric field or an electric potential. And then when wire 1 creates a magnetic field and wire 2 responds by creating electron flow, that electron flow has its own magnetic field, and for a moment those two wires will be repelled. So if you have wire 1 laying next to wire 2 and you put power through wire 1, wire 2 will be pushed away just for a second as the electric flow is created in the second wire. And then when you turn off this one and you get another electromagnetic force over here, it will get pushed away again. So the repulsion force between the two is a reaction between two opposing magnetic fields in an induced electron flow. Okay, let me show you some pictures, and hopefully that makes sense, and then we'll be done with this unit of the chapter. So here I have a battery hooked up to a loop of wire and a switch. When I close the switch, an electromagnetic field is created here as the electrons flow, and that created electron flow, the created magnetic field will induce, for just a split second, an electron flow in this wire in the opposite direction. Now remember, wires that have electrons flowing in the same direction are attracted. So in this case, the wires have electrons flowing in an opposite direction, so they're repelled. Okay, so the electrons are induced to flow in the opposite direction in the second wire, and so there's a repulsive magnetic force. You get a little bit of a current flow that would read on an ammeter or a voltmeter, and the wires would bounce away from each other just a second, and then you'd be able to open the switch and get another change in the magnetic field and another change in the electron flow, and that would bounce out again. So every time you close or open the switch, you'd see a movement apart of these wires and a slight bounce on the ammeter needle. Just another representation of that. If current 1 in the wire is going in this direction and we induce current 2 to have a field in the opposite direction, then they're going to have a repulsive magnetic field interaction and move apart from each other. Okay, there you go. That's it for 22A. Let me know if you have any questions. Please, you can put them in the comments field below and I will address them as quickly as I can, or I'll see you tomorrow in class. God bless you. Have a wonderful day.